If you look at the rotational equilibrium problems, number 6, you got two painters, there's a bucket, they're all on a scaffold, and they're supported by two cables. Now you're given the dimensions of the scaffolding, given the locations of the painters, and the bucket itself. And using all these forces, you can determine the tension in each of those cables. So what we'll have to do is diagram out where each force is applied to the scaffold itself, and then once we do that, we can take our approach just similar to the board supported by two ladders from underneath. So let's take a look at how we do this. Alright, so if I end up drawing out my scaffold, looks like it's 3 meters in length. And first painter is about 1 meter, or exactly 1 meter, so I would say right about there. You got him there. The bucket, it says, is at 2 meters, so we're going to go 2/3 of the way there. There's a bucket right there. And then the last painter is 0.5 meters from this point here, so 2.5 all the way. So we'll just put them here. And, you're going to find that your drawing doesn't actually need to be perfect to solve this. But what we do need to recognize is that there are several forces being applied here. You got cable 1 here, let's call it tension of cable 1. You got cable 2 here, tension of cable 2. Alright, so 2 tensions here. We also have a force of gravity from the person. Their names are Bob and Joe. I'm not even going to be able to keep track of this. Bob weighs 750 newtons and is at 1 meter. So this is Bob. 750 right here. And we gave him his weight, not his mass, so we're in newtons. Easy enough for us. The supplies, the paint bucket, that is 500 newtons right here. And then the other person here, which is Joe, he is 1,000 newtons. And so you got your 3 objects that are on the scaffold, and what we have to recognize here is that the scaffold itself also has weight to it, and you're actually told what that is, and this does matter here. Its weight's directed at the center of mass here, and it is 345 newtons. Looking at those forces, we've got 2 unknowns here. Choosing your pivot point is going to allow you to approach this here. So, long story short, let's label this out 1 meter here. I'm not going to label that one, but I will label, I guess, the full 3 meters. We should recognize that that center of mass is at 1.5 meters. This one's at 2 meters away. A lot of things to keep track of here. And then this guy, this is 0.5 meters. Which would make the other distance 2.5 meters. We'll end up taking a look at both of those. Because you have 2 unknowns, torque is really going to be the best bet to solve for one of the unknowns. In fact, it is totally necessary here. So always choosing your pivot point on top of one of the forces itself will eliminate the torque from that force. So if we make this our pivot point right here, we eliminate T1 from the rotational equilibrium expression that we're going to generate. Now looking at these torques, if this is our pivot point, this would cause counterclockwise rotation, this tension here, whereas these 4 vectors here would all rotate this clockwise. Now they'll have to be balanced out because nothing here is falling. Sigma tau equals 0 here. And we'll say that, okay, T2, that's our positive torque. Tension of 2. How far away is that? That's 3 meters away. This is balancing out all those negative torques here. So what we have here is the force of gravity here, which is 1 away. So 750 times 1. You got the force of gravity here, 345. That's halfway across scaffolding, 1.5. We got 500 newtons at 2. And then we got 1,000 at 2.5 away. Run out of space here, times 2.5 down there. Alright, now let's see what I end up getting for my answer here. So 0 is our net torque. We have T2 here, and that's 3-way, minus 750 times 1, minus 345 times 1.5, minus 500 times 2, minus 1000 times 2.5. Let's see if I get the right answer here. We get that T2 is equal to 1,589.17 newtons. And looking at the number of this problem here, what do we have here? This is number 6 on the rotational equilibrium packet. So if I scroll to the back, our answer key here, and I get 1,589.2 on the answer key as our value for T2. So it looks like, you know, we're on the right track here. Now all we got to do is solve for T1 here. T1, there's two ways you can approach it. You can choose this as your pivot point and balance out all of these torques here. You would have 4 counterclockwise and 1 clockwise here. And the other option is simply to go with a net force equals 0 here, because this is also in static equilibrium. So if you do a sigma F expression and make it equal to 0, it's T1 and T2. Those are up. 750's down, 345's down, 500's down, and you got 1,000 down. Since we now know T2, T1 is our only unknown. So this is probably the easier way to do it. But regardless of which way you choose, you should still get the right answer. See what we end up getting here. Alright, so T1 is unknown. T2 we just determined to be 1,589.17. 750 is down, 345 is down, 500 is down, 1,000 is down. And what I end up getting is 1,005.8 for T1. T1 equals 1,005.8 newtons, and that is consistent with my answer key, so that's a good sign there. Out of most of the problems here, I think that was one of the ones that look, I would say, a little bit more foreign to people, and I would say a good one for us to be able to solve, to understand how we can use rotational equilibrium to analyze a number of scenarios, and this is just one of them.